So here, this is really, as you can see, chapter 1 of the material, and we're going to have like 4 or 5 days of the introduction to give you a broad overview of everything, and then we're going to get into maybe deriving the basic equations and get to boundary layer equations and turbulent boundary layer equations and define the closure problem and more like physics-focused discussion. Once we do that, then we'll try and close these systems of equations and talk about different models. And a lot of the models we're actually talking about are available in CFD codes today. So if you use the CFD code, commercial one, you can see there's lots of options like SST, K omega, K epsilon, algebraic models, LES, DNS, different LES closures. And so you'll actually know what those means and kind of know where the equations of physics and assumptions come from. At least that's the hope at the end of the class. So here in 1.1, I've written all this. So sometimes I'm reading, sometimes I'm going to be writing in here and can note it with me. But we're going to look at some of these overviews of the closure models. So closure means that there's basically more equations and variables than there are terms. And it's our aim to try and find ways to make the number of variables and equations equal. And that would be closure. And the majority of this turbulence modeling world revolves around this word right here, Reynolds average Navier-Stokes. And Reynolds averaging, which we'll show later, is nothing but something like U equals U bar plus U prime. And this could be any variable. This is a velocity component. Here, U bar is nothing but the average variable. So you would take like a time average, and the prime is the fluctuating variable. And this was really introduced by Reynolds in 1895. Well, he didn't introduce this averaging technique. It existed before, but he applied it to the Navier-Stokes equations. So I'll just write NSE. And of course, this was published in his work on turbulence. And this was really a pioneering work which exists and even as a reference today, but it's so common that people just say Reynolds average Navier-Stokes. It's an unsteady equation. And if it's a steady equation, you would say steady RANS. And in this class, we're going to derive the RANS equations from the Navier-Stokes equations. And of course, this just had a profound effect on everything we do in CFD and turbulence today. And you probably hear from the CFD and AIAA communities that there's generally 2 major ways people do CFD for turbulent flows. There's large eddy simulation, which is filtering, and there's the steady RANS, which uses this basic property for all the variables are decomposed. So this is the Reynolds averaging technique. Now, a little bit before that, someone named Boussinesq, and I'm going to have to spell this right, Boussinesq, I believe, 1877, he introduced what we call the concept of eddy viscosity. And as of Reynolds, his name is so popular today in the turbulence community that we don't even really reference his papers anymore. I'm sure if we did, every paper on RANS modeling and turbulent flow would reference these 2 papers, and they have tons of citations, which would definitely increase their citation count. But at some point, if you do something and the scientific community is so popular, people just kind of say, oh, it's, like Einstein's theory of relativity. You don't need to reference it in your papers. So this is basically the idea that you have some enhanced viscosity in your flow. And so as early on, they said, well, turbulence is like a medium. It's a different medium of the flow. And it might just have a higher effective viscosity. And so we would often call this variable epsilon sub t. And that's how it'll be shown in the majority of the equations we're going to see. So that'll be the eddy viscosity. And when we start to get into more equations in the class, you'll see that's what we have. So I wrote here, neither Reynolds or Boussinesq attempted a solution of their equations in any kind of systematic manner. So Reynolds took Boussinesq's approximation, and he also did his decomposition, which I wrote up here. And he put it in the Navier-Stokes equations and simplified them for incompressible flow, and that was it. And he published it. And he did pose a closure type problem, and I guess he left it and maybe attempted some solution approach informally, but he never closed the equations. And to close the equations, you have to actually create more equations, and that's what the turbulence models actually do. And of course, that's kind of a problem. And it should be noted, part of the reason was they didn't know the physics. There wasn't any really great experimental database. So experiments and physical insight were limited. And another 150 some years of mathematical development. So that was another problem. And so there were two camps, right? There was sort of a mathematician camp who did theoretical work like d'Alembert in France, and there's these experimentalists. And Reynolds was a rare person that he actually did, Osborne Reynolds, experiments and this mathematical development. But he's much better in terms of experiments. And here's a famous schematic, which I stole from an early paper, and it's titled, of course, Figure 1.1, and all the figures will be labeled with equations, experiments of Reynolds. So let's just look at this together. You can see here, this is a schematic of this here, and this is called like a trumpet nozzle. And why is that? Because it looks like a trumpet, of course. So, any musicians in here? Trumpet players? Yeah. Well, my parents tortured me in high school playing trumpet, so that brings back kind of scary memories of my musician days. And your ears would also be insulted if I played for you. So you can see in here, he basically injected a dye, another substance, and used the spark emulation and illuminated the flow. And in the laminar flow with low speed flow, in this carefully constructed tunnel, he would see just a steady line, and that's a nice laminar flow, right? There's no fluctuations. So if you go back to his decomposition, U equals U bar plus U prime, I would not expect to see any U prime variable at all. So U equals U bar, it's a laminar steady flow. Then, of course, what happens? He increases the speed. What does that do? That increases Reynolds number, which is something like what? Rho UL over viscosity. Viscosity is the same, L is the same, density is the same. And so he's only increased velocity and then increased Reynolds number. So remember, Reynolds number equals what? Rho UL over mu. So this is a mu, that's viscosity, density, velocity, and length scale. So hopefully everybody remembers Reynolds number. I think everybody probably in this class does, because you got to be a little gutsy to take a class like this, I think. So I admire that. So that's transitional flow. And then, of course, in the third experiment and these are original diagrams reprinted in a later paper. So these are Reynolds writing. You can see right here, they're starting to become the breakdown in fully developed turbulence. So you went from a laminar flow into transition into full turbulent flow. In the transitional flow, he say, oh, well, he can predict the onset of transition because there was a critical Reynolds number. And if the Reynolds number is greater than the critical Reynolds number, then what happens? Our flow transitions into a transitional flow. It might come on and off of instability waves. If it's even higher, then, of course, it's amplified, and these instability waves break down into fully turbulent flow. So that's the experiments of Reynolds and his major contributions, at least to this part of the field. And my notes are a little bit offset from yours because I had a lot of trouble with LaTeX. So I'm sorry about that. But so what happened many years later is one person named Ludwig Prandtl, who was a German, he made a big breakthrough. And not only did he, of course, invent the idea of boundary layers in a conference paper in the earlier 1900s, but in 1925, he introduced something really important to try and close the RANS equations so we can make predictions of turbulent boundary layers. And he introduced the idea of this mixing length analogy, in that there's some sort of length scale, L, and it's somehow related to an eddy viscosity. And then you could say, well, let's write it as mu sub tau. And then the total viscosity would be viscosity plus mu sub tau. And so how do you find that relation? And he might just use simple dimensional analysis. And those models, all the models that came out of Prandtl's 1925 paper are often called length scale models because he's trying to model some length scale. And that length scale might be related to the one of Osborne-Reynolds, maybe. And there's many different ways we can define like length scales of turbulence. So this is what we call the mixing length hypothesis. And it can be good or bad, depending on what you want to do. And in the model that we're going to program in our computer code this semester will be this type of algebraic model. Why? Because it's simple to program and modify laminar boundary layer flow codes. And it's also, once you do that, you can also increase their fidelity through algebraic models, differential models. And this like dominated everything for the next 20 years in the world of turbulence modeling. And he had a student named Theodore von Karman who moved to the United States. And how many people have heard of Dr.? Okay, got 1, 2, few, 3, okay, 4. Yeah, that's pretty about half the class. That's pretty good. And he came to California and he founded the NASA Jet Propulsion Lab. And he was very famous in our country and around the world, and they even made a stamp of him. I have a friend who was over at Cornell, and he actually sent me a picture of the stamp. I should have put it in the notes. And what did he do? Well, he basically created a model based on this mixing length hypothesis, and he basically created the first practical zero equation model. But of course, it was just on paper, and nobody could evaluate it, right? Because we didn't have digital computers back then. And we call these zero equation model. Why? Because there's no differential equation. It's an algebraic equation that just, in this case, would represent some sort of length scale with the eddy viscosity. And that was dominant for a while. And in 1945, Prandtl published a paper in Germany. And what else happened in Germany in 1945? Well, there's the downfall of Germany after World War II. So while the world was burning around him and being firebombed and his university was being dismantled, he was sitting in his office publishing papers on turbulence models. And you'll actually see a similar theme through this course in terms of the history of modeling that people get involved in are slightly crazy and seem to be working when the world's burning around them. And there'll be a Russian investigator we'll talk about in a minute who did the same type of thing. And you should read this little bit of text. I'll just read it for the class. I wrote, to improve the ability to predict properties of turbulent flows and developing more realistic mathematical description of turbulent stresses, Prandtl postulated a model in which the eddy viscosity depends on the kinetic energy and, of the turbulent kinetic energy. So K is the energy in U prime, which are the turbulent fluctuations. And we are welcome to define energy however we want, but I think it'll be wise to try and derive this from the equations of motion after we do Reynolds averaging. And it'll probably involve something like U prime, because that has the values of what? Meters squared per second squared, I believe, which is like a value of energy. So this model, which was proposed by Prandtl, was the first partial differential equation model which approximated turbulent kinetic energy. And people have evaluated this model today. It's not perfect, but he's definitely credited with deriving this equation. And we'll show that equation in this class too. Okay, another interesting thing is now that we have these eddy viscosities and depend on the flow history, we need to provide a more like physically realistic model to find the length scales, because before that, length scales were basically defined like as say the distance from the wall. So how do people do that? They might say that viscosity has dimensions of, say, velocity times time, t. So that'd be meters per second and second. That can't be right. Oh, sorry, this is length. Right, okay, now that's right. That gives us meters squared per second. And we might think of like a length scale as a characteristic eddy size. So what does that mean? When we look at turbulent flows and pictures of turbulent flows, we might see different eddies, big ones and small ones. And so the distance here across like an eddy might be L, something like that. And the problem with these approaches is that you would need to know something other than the initial conditions and boundary conditions of the flow. And that's why they're called incomplete models. So an incomplete model is, really I define it right here in my next point. You can see it's better that I type things out than write them. Is one where we have to define something that we're trying to find about the flow before we do the calculation. For example, if I'm trying to predict a turbulent flow, I don't really know what the size of the eddies are. But all these models that Prandtl and von Karm and all these guys formed were all incomplete, because I had to know something about the solution before I had it. So that's really the difference between the complete and incomplete models. So what would be one example? Like if you're doing a turbulent boundary layer flow, you might look for the boundary layer thickness, or the length scale is a function of y for boundary layers. So these are two examples where we absolutely have no idea, but we specify something in the flow. So one good model actually turns out to be L goes as y. And you can see it's dimensionally correct on both sides. We have meters on both sides. And that's pretty interesting to me, because it's just saying that the maximum length of a turbulent eddy in a boundary layer flow just goes as the distance from the wall. And you'll see in some of the most popular models today, like Spalart's model, a one-equation model, which we'll discuss in this class and look at solutions of, uses basically the minimum distance to the wall is like some length scale. But then you can say, well, there's problems with that. Like what if I have a shear layer? A shear layer has no wall. It's just two speeds of a flow next to each other that are different speeds. How would I define a length scale in advance for a shear layer? It's definitely a self-similar flow like a boundary layer, and I might just say, well, it's something like the thickness of the shear layer. But then I have to say, well, the shear layer has some spreading rate. In this case, I have no way of really doing it in advance. I have to make some assumption about the solution. So that's a problem. And now it turns out that an ideal turbulence model, like it'd be much better if I didn't have to know something in advance about the flow, right? Like I don't know what the length scales are. So ideally, I don't have to specify something about the solution in advance. Right? That's definitely be a wonderful thing. And any model like that, these are sort of informal definitions, but any model like that would be called a complete model. So this is really the definition. And there weren't any complete models, because to have a complete model of turbulence, you need to have some more differential equations to find these properties that are coupled in with, like, say, densities, velocities, pressures, temperatures, etc. And then there's, of course, one of my heroes, the great academician Andrei Kolmogorov, who's probably the best Russian mathematician who ever lived. And he published a paper not long after his famous K41 paper in 1942, a year later. And that paper essentially had the first K omega model. And you're going to see this word a lot in this class. So K is turbulent kinetic energy. And omega is specific dissipation. And this is a two-equation model, which is also interesting. Here, omega has the units of per second, generally. And that's the rate of dissipation of turbulent kinetic energy. So he wrote down 2 extra partial differential equations, and they're solved with the RANS equations, and that would give you a solution, hopefully. And people have also evaluated Kolmogorov's model today of modern computers. But you can see that was published in 1942. And just like his co-worker Prandtl in 1945, he was also working on these things, but they didn't know about each other's work because the Russians and Germans were killing each other, if you didn't notice, in World War II. And he published this model in basically his office was a bathroom in Moscow in a shelled-out building with no water and no electricity, and this is what he was doing. He was still working with his students. It's quite an interesting thing. So this is a whole class of models that came out of this, and they're generally called the two-equation models. And they all started with Andrei Kolmogorov. And we're going to have a module on two-equation models. Okay, yeah, about 15 minutes left. That's okay. Less known people today in terms of fame outside the turbulence modeling community is models that do not use the Boussinesq formulation. And these are much more rare, and we won't focus much on them in this class. So almost all these commercial CFD solvers are looking at Boussinesq approximations, and we'll look at mathematically what exactly that is today. So that's something important to remember. So we call these the stress transport models sometimes. There always seems to be like an exception for every rule. And they also involve what we call second order closures, which means that we're trying to close even more equations. And typically, unlike a two-equation model, they have 3 or more equations. And in the most typical formulation, you'll see that for a 3D flow, we'll have 1 equation for turbulent kinetic energy, which I'll call K, so turbulent kinetic energy. And probably 6 components of what we call Reynolds stress. And you might be sitting here thinking like, oh, I don't know what the Reynolds stress is. You might just think of it as like, well, there's a viscous stress tensor in the Navier-Stokes equations. There should be some sort of equivalent turbulent Reynolds stress in a RANS set of equations. And it turns out that if you assume that a tensor, a 3x3 tensor, is symmetric, then there's only 6 unknowns because, of course, the terms on the other side of the diagonal are equal to the terms on this side of the diagonal, if you will. So there's really 6 unknown stress components, and they solve the same turbulent kinetic energy equation that was formulated a long time ago by Prandtl. And of course, there's disadvantages and advantages of all these models, and we're going to look at some of these stress transport models as sort of like the last part of the class. It's nice to have like a more general model, but the problem is you're going to have more terms that you need to close. And it can be shown that even if you try and do that rigorously, you just develop more and more terms. In fact, there's a mathematical proof that you can't close these types of models without making some kind of assumption. And that lies in the whole problem of the turbulence problem we call it today, like in mathematics and physics. It's the turbulence problem. The big advantage, of course, is that you have made less assumptions and you have more terms you can play with. And technically, you should be able to predict all kinds of flow physics, which you wouldn't be able to predict ideally with 2-equation or 1-equation models, like separation, strong curvature, strong adverse pressure gradients. And to calculate those types of flows with traditional models like Kaplan, K omega, 1-equation models, you actually have to add more terms to the models. There's more empiricism. So technically, with these types of models, you shouldn't have to do that. But it turns out that since they're more computationally intensive, people have spent less time examining them. So let's just kind of make some notes about these 4 types of models and their major developments. So this is section 1.2. And we already mentioned some of these, right? Algebraic models, we call them 0-equation models because there's no differential equation. 1-equation models have a single differential equation. And I should mention that between here, there's something called the half-equation model, which there's one famous by a professor and a student of Johnson and King, and we'll mention that briefly, but it's rarely used today, but it was very popular at the time in the 70s. Then there's 2-equation models, right? Those solve 2 differential equations plus closure coefficients, and the stress transport models, which aren't as used as much today. So usually if you're running CFD codes today, like in industry, if I was asked to find the flow over an aircraft, I would probably choose a 1-equation model because 2-equation models are a little more expensive, and I only have so much money for computers. If I'm looking for like a jet flow or some more component flow, I probably choose generally 2-equation models. And because they're very robust, they're complete models and less computationally expensive. So let's just look at the algebraic models. Note there's a few that we want to talk about in this class, and one is going to be of Cebeci-Smith. And Cebeci and Smith were 2 professionals working in an American aerospace company. We'll get into that later. And this is nothing but an eddy viscosity mixing length model. And we're going to look at their model closely because a lot of the aircraft in the 70s, 80s, and 90s were completely developed with their models. And in fact, some people today call it the integral approach or Cebeci-Smith integral approach, and it is very popular. Another one is Baldwin-Lomax, which I believe came out in 1978, according to my note. And this is an algebraic model, which is actually a true algebraic model, unlike Cebeci-Smith, who makes some assumptions. And this is the model that we're going to program in our computer code in the last part of the computer project. And you'll see it's so popular because if you had a code that solves the Navier-Stokes equations, the laminar flow, all you have to do is add in one little equation to the whole thing to make it turn into a turbulent flow solver. And so the hardest part of the computer project is actually the third one, where you develop the laminar flow solver, because we'll be solving the Navier-Stokes equation with a marching technique. And then to modify that in a turbulent flow solver, all we have to do is add a few lines of code. So that's a little hint for the future. Okay. 1-equation models, as I mentioned, are very, very popular today and probably have enjoyed the most success. One that we'll be talking about the most is probably Spalart-Allmarus. And both these people are alive and well today, and I wouldn't say we're friends, but I've acquaintances at conferences, so it's kind of neat to run into someone well-known. Spalart's a Boeing technical fellow, and Allmarus works at MIT out in Seattle for Boeing. I guess he just gets a different paycheck. And this is a 1-equation model, and they love 1-equation models, and they were really developed for predicting flows over entire aircraft. That was their original goal. And they are probably like available in every CFD code that I've ever seen. And a lot of people make sure Spalart and Allmarus models in there. And a lot of people have done research since 1992 to extend their models, and there's many corrections. And we'll look at the NASA turbulence modeling website when we talk about Spalart's model, and you'll just see how popular it's become. Other reasons it's popular is because it's easy to program and implement and validate. So one thing I've seen with turbulence modeling is if you can create any model you want, anybody in this class, but the problem is to get it accepted in the community. So one reason it was successful was because it's easy to program. And something that's easy to program, even if it's not as accurate, is sometimes more valuable than something that's hard to program and more accurate. And that seems strange, but that's what the aerospace community has done today. The other super popular model is the Mentor's K omega or Wilcox variant, and we'll look at this model too. And that's actually a more accurate model. Oh, excuse me, that's a two-equation model. Gotta put a line here. And remember, these are two differential equations. And you can see this one, the one by Mentor or Wilcox, and we'll look at these in detail in some of their solutions, solves K omega or K epsilon. And they usually always solve turbulent kinetic energy in one differential equation. And most people choose all kinds of other things. But there's also lots of variants we're not going to talk about because they're hardly ever used or specialized. And sometimes, you know, they'll solve something like length scale or a time scale, tau. So there's no reason that you can't formulate a turbulence model that doesn't, you know, that solves other variables. And then you can rederive variables that are maybe more useful, like epsilon, which is dissipation. It also is true that in these models, K omega and K epsilon can essentially be derived from one another, and there's relations. So when I was in NASA, I used to solve K omega models, but people wanted epsilon, the dissipation, so I would convert omega to epsilon with a single line of code. No big deal. As I mentioned, the stress transport models are just huge, and there's just way too many to detail. But as they have large number of equations, they are way more complex. It's probably Noah Zambrano starting to realize. And they're in very few applications of CFD. And like I mentioned, we'll be looking at some of these. And we'll try and look at the Mentor SST model for shear stress transport. It's probably one of the most popular and robust models, but it could be considered a two-equation model or a stress transport multi-equation model, depending on, I guess, how you categorize things. So without getting too long in this first class about the introductory material, I just want to make some final thoughts, and you'll see this is kind of a bewildering thing. Because if you're going to go into turbulence modeling, you first have to say, well, which area would I want to be in and why? And there's definitely different levels of difficulty and even acceptance in the community. For example, if you're creating a new algebraic model today, nobody will pay you to do that and wonder why, because there's already a ton of algebraic models that are well developed and well validated. So most research and most work in the field is in these two-equation models and stress transport models. And then there's a lot of people in the federal government who say, I don't care about any of this business anymore. I just want to do large eddy simulation, which is a whole nother topic. But we'll have a few classes on LES near the end of the semester so you can get some of those things. So you can see there's generally 4 categories of models here. I guess I should have written a 4. Right. And there are more failed attempts in turbulence modeling than there are publications, because generally you only publish research that has advanced things and that's correct. So many failed attempts by people a lot smarter than me to create new and excellent models. And I would say that new ideas are always welcome. And if you have a good idea, it would get funded and you would be able to do the work eventually. I was told by a NASA chief scientist of Langley once that all good ideas are funded eventually. And then he told me to leave his office. So we're looking mainly at concepts in this class that were successful. And maybe I should write mainstream. Hopefully you can read my writing. It certainly beats writing on a chalkboard. So that's the overview of the first class and the 4 major types of models. And I haven't really defined or gotten to what LES is, but we'll look at that too. And a little bit at one class on DNS. And so my recommendation now is to look over the computer project assignment. And they're not really assigned formally yet. What I'm going to do is we're just going to have one whole class where I talk about each assignment. So there'll be 4 classes on how I talk about the computer assignment and how I would do it. And I'm just going to spend the whole class trying to teach you how to do it. And then you can go off and try. And it's okay to fail. And just warning you, the first, it took me many years to actually complete it correctly. And that's okay, because it is pretty difficult. Okay? Does anybody have any questions today? No? Okay, good. And let me know. You can send me a Canvas message or email if you have any things we should change about the format of the class. This is small, and dialogues are really welcome. And get to know you more this semester. That's a great thing about a small class. So thank you so much for your time today, and I'll see you Tuesday.